Good afternoon, all of you. Today I'm going to talk about the size effect on fatigue performance. This is the outline of my talk. And in the beginning, I would like to mention briefly what is specimen size effect. It means that for large specimens or for the increasing of specimen size, the mechanical behavior, especially the fatigue performance, will reduced. So that's the size effect. In fact, about 5 years ago, Da Vinci did the first experiments to show the size effect. And this is the drawing. Perhaps some of you attended the plenary lecture by Francesco Vieco. He also saw a similar similar drawing, but not this one, very similar to show the size effect by Da Vinci 5 years ago. So he stated that the shorter the metal cable, the heavier sun it can carry. So that's the meaning of size effect. And of course, in recent days, the results showing that the small size specimen, large size specimen, small size, large size. So that's the size effect. Small size specimen has higher mechanical behavior, especially fatigue performance. So the question is, how can we use the data of small specimens to estimate or to predict the fatigue performance, especially of large size specimens? So this is the question, or also the topic of my talk today. Sorry. And we designed 5 groups of specimens by additive manufacturing. That's Pi64. And these are the processing parameters to give the laser energy density of 76.2 joule per cube millimeter. And the second plenary speaker today just now asked me if I have questions. I said, yes, I have many. And one of these is, what is the energy density he used? But he's not here anyway. And this density, energy density, is a kind of optimized values to give this value. Anyway, we have 5 groups of specimen, from the small one of 3.5 millimeter in diameter, and the largest one is 18.6. And the related control volume is about 46 cube millimeter to about 700 cube millimeter. And then we perform the fatigue testing with 20 kHz frequency and -1 stress ratio. This is the general fatigue data to show the fatigue performance of large specimen and the small specimen there. So it's a kind of obvious specimen size effect with the increase of specimen size, fatigue strength decreasing gradually. And the question is how to categorize, how to describe this kind of size effect. And we use a concept of probabilistic control volume method. And in previous study, we use this kind of concept to categorize the size effect of ordinary or conventional materials. In this concept, we assume a large specimen is a combination of the number of small ones in terms of control volume. And the fertility life of large specimen is the minimum of the small specimen. And also we assume the fertility life, the fertility life is the small specimen at the stress level with vapor distribution, like the formula here. And then we are able to write the following expressions of cumulative distribution of fertility life for large specimen here. Again, this is our previous work to show this. And specifically, at the same survival probability for arbitrary specimen A and C, we can write this formula to show the fertility life of the two types of specimens as a function of specimen size. And because the VC here is very small here, the small specimen is quite small. So the number can be written as this expression. And then we can write for fertility life of two types of specimen is a function of the ratio between the two types of specimen. And if we consider two parameter vapor distribution, and the formula is easily to be shown as this. And similarly, for stress, we can also write a similar expressions to characterize the size effect. Again, we have to emphasize this method or this result is to characterize the size effect for conventional material. And now we are considering the case for additively manufactured material. And one of the major features is that for such kind of material, it contains large amount of defects. So we add a term of this we call T here to consider the large amount of defects in AM material. So after this, we are able to write we call modified model or modified expression. This is the original one. And then for AM material, we add a term here. T is written here, is S sub S over S sub S. And this the area of large specimen and area of here, the small cross-section area of large and small specimens. So again, this is the modified one by adding a term of this to consider the large amount of defects in AM material. And we use this modified expression to estimate our experimental results. I saw previously. And here is the type 1 as reference source to predict or to estimate type 2, 3, 4, and 5 here. So the curves are the estimations by the model, and the data points are from experiments. We can see the predictions or the estimations are reasonable or quite good. And we can see this figure, the dash curves are by original one, suitable for conventional material, and the curves are the modified one. We can see the modified model is better than the previous one. And again, we use the type 2 as a reference source to estimate type 3, 4, and 5. We saw good estimations. And further, we use type 3 as reference source to predict type 4 and 5, and type 4 as reference to predict type 5. So all we can see are quite reasonable. And also we did a calculation of the error for two models. The blue ones are due to previous or original one, and the red ones are due to the modified one. We can see the modified one has better estimation with good or with small errors compared with the original one. Okay, now, sorry. And then we would like to extend our model. This is the original one, and this is the modified one. I also emphasize we add a term here. And we can consider, or we can write the volume or surface or area as a function of diameter. For this or from this, based on this, we can write the original model and modified model in terms of diameter of specimens. And after this, we can see that there's a coefficient there or exponent there. We call this size effect sensitivity factor, SES. And for original one, this factor is -3/k. For the modified one, is -2 alpha plus 3/k. And this for two types of materials. We may use other terms of SES to characterize the other types of materials. So it's a kind of general model to describe or to characterize or to address this issue. So I conclude my talk. I mentioned we use this modified model by adding this term to estimate the size effect of AM material. And also we try to write this general form with a sensitivity factor to characterize size effect for different type of materials. So thank you very much.